Hello everyone and welcome back. Over the last few sessions, we have built a solid foundation. We have learned that the Froude number dictates the personality of a flow, whether it is slow and deep, which we defined as a subcritical, or fast and shallow, which we defined as a supercritical flow. We derived the speed of surface waves by a relationship c is equal to under root gy, which is the fundamental speed limit for information on the water surface. And we explored the uniform flow where the gravity and friction are in perfect balance. But here is the thing, the most real channels are not uniform. The bottom slope changes, the width also changes, and there are obstructions also. When these changes happen, the flow depth and velocity adjust. The question is, how do they adjust? What are the rules governing these changes? So today we are going to answer that question by looking at the energy of the flow. In fluid mechanics, energy is like currency. It can be exchanged between different forms like potential energy, kinetic energy, and it can be spent through losses like friction. Understanding this energy balance is the key to predicting how water surfaces rise and fall. So we will introduce a powerful new concept called specific energy, and we will use it to unlock the secrets of flow transition. So let us begin. Let us start by writing the energy equation first of all for a reach of an open channel. Look at this particular figure. We have two sections, 1 and 2, separated by a distance L. So the channel bottom has a slope S naught, which means the elevation drops from section 1 to section 2 is S naught times the distance L. We assume the velocity over here is uniform across each section, a one-dimensional approximation, and we also assume that the pressure is hydrostatic. So the pressure head at any point is just the depth of the water above it, which we denote here as small y. Now recall the energy equation from our earlier fluid mechanics, which includes the head loss. Applied to our channel, it looks like this particular equation in which we have the head loss term HL. Since the pressure is hydrostatic, so we can assume the terms P1 over gamma equals to Y1 and P2 over gamma equals to Y2. So we also can write the third term as Z1 minus Z2 equals to S naught times L. So we can rewrite this above energy equation, which we have seen, into a more simplified equation for the open channel flow. So this is our fundamental energy equation for open channel flow. It tells us that the total mechanical energy at the section 1, which is the sum of the water depth, namely the potential energy relative to the bottom, and the velocity head, is equal to that at the section number 2, plus any head loss adjusted for the change in the bottom elevation. So if there is no head loss, the energy line is horizontal and the total energy is conserved. But in reality, there is always some friction. We often represent the head loss per unit length as the slope of the energy line, called as a friction slope, which we denote as capital S subscript F. So HL would be equal to SF times the distance L. Now, here is where we introduce a concept that will become very important in open channel hydraulics. It's called as a specific energy, denoted by the symbol capital E. Specific energy is defined as the energy of the flow relative to the channel bottom. Mathematically, it can be expressed by this particular equation: E is equal to y plus v square over 2g, and it's just the depth minus the velocity head, depth plus the velocity head. It represents the total mechanical energy per unit weight of the fluid measured from the channel bottom as a datum or as a reference. So why is this so useful? Because it separates the local flow conditions from the elevation of the channel itself. It allows us to focus on what is happening in the water independent of whether the channel is going uphill or downhill. So now for a rectangular channel of width B, we can write the flow rate per unit length as Q small q equals to capital Q divided by small b equals to V over V times Y. So V equals to Q over Y. Substituting it into the specific energy equation would give us the simplified equation for the specific energy, which is represented by this particular equation. E is equal to y plus q square divided by 2g y square. So this is a powerful relationship. For a given flow rate per unit depth q, the specific energy E is the function only of the depth y, and this function has a very interesting shape. Now look at this particular graph. This is a specific energy diagram. The horizontal axis is the specific energy E and the vertical axis is the depth y. The curve you see in this equation uh, written on the right hand side of this on this graph plotted for a fixed value of q. Notice something immediately that for a given value of e, say at some value greater than a minimum, the vertical line intersects the curve in two places. Now that means for a given flow rate and a given specific energy, there are two possible depths at which the flow can occur. One, the depth is large and the corresponding velocity is small. So this is the slow and the deep branch. The second is that the other depth is small, the corresponding velocity is large. This is the fast and shallow branch. Now these two depths are called alternate depths. They are two completely different flow states, but they both have the same total specific energy. So as the specific energy E gets very large, the upper branch approaches the line y is equal to E. That's the limit of a very deep, very small, very slow flow where the velocity head is negligible. The lower branch approaches y is equal to 0, the limit of a very shallow, very fast flow where the depth is negligible compared to the velocity head. Now, but the most important point on this curve is the nose, the point of minimum specific energy uh, is E minimum. So this is where the two branches meet. At this point, there is only one depth possible. So let us find that point mathematically. To find the minimum of the function, we take the derivative of the specific energy with respect to the y and set it to 0. And solving for the y and plugging it back and into the specific energy equation, we can find out the beautiful connection to our earlier work, which gives us the relationship yc equals to q square g raised to the power 1 by 3 as represented in this slide. So and then the q square would be equal to gy raised to the power cube. But since q equals to vc times yc, so we can write the simplified equation as vc equals to g times yc under root. Now, have you identified this particular term which now we have find out mathematically, which is the under root gyc term? So that exactly the wave speed c at this depth. So at the point of a minimum specific energy, the flow velocity equals the wave speed. The Froude number is exactly 1, This is the critical flow. Therefore, the upper branch where the depths are greater than yc and the velocities are lower corresponds to the subcritical flow where the Froude number is less than 1. But the lower branch, where the depths are less than yc and the velocities are higher, corresponds to the supercritical flow. Here, the Froude number is greater than 1. So, the specific energy diagram has given us a complete picture of the possible flow states. Now, let us see this in action in with a real problem. We have a water flowing up a ramp, and the channel is rectangular and has a constant width. The flow rate per unit width is given Q equals to 5.75 feet square per second, and the upstream depth Y1 is given as 2.3 feet. There is a ramp that raises the channel bottom by zero point 0.5 feet. We assume no energy losses, friction is negligible. We are asked to find over here the water surface elevation downstream of the ramp, which is Y2 plus Z2. Since there are no losses, you can use the Bernoulli equation, which is just the energy equation with the head loss equals to 0. So we set up our datum, which is Z1 equals to 0, and then Z2 is given, which is zero point 0.5 feet. We know Y1 equals to 2.3 feet, and we can find the V1 from the continuity, which comes out to be 2.5 feet per second. And so plugging these numbers in with a g value of 32.2 feet per second square, we can simplify and we can get the final V2 as 5.75 per Y2. So substituting equation, the first equation, this particular equation into the first equation, and after some algebra, we get a cubic equation of Y2. So solving this cubic has three roots. One is negative and physically meaningless, the other two are positive. So Y2 has two values, 1.72 feet and 0.638 feet. So which one is correct? We have an interesting question over here. So this is where the specific energy diagram comes to rescue. So uh, now look at this particular figure. This is a specific energy diagram for our flow with Q as 5.75 feet square per second. We can plot our upstream condition at point number 1 on this diagram, which is at y1 equals to 2.3 feet. We can calculate the energy, specific energy E1. Plugging in the numbers gives the E1 as 2.4 feet. So we can also found that our downstream condition. So our energy equation told us that Z2 minus Z1 is zero point 0.5 feet. So we can easily calculate the E2 equals to E1 minus zero point 0.5. So it gives us E2 as 1.9 feet. So our downstream condition must lie on the specific energy curve at a point where specific energy is equal to 1.9 feet. As we saw that these are 2 points on the curve with that specific energy, one on the subcritical branch, which is deep, which is point number 2, and one on the supercritical branch, which is shallow and point number 2. So here is the key concept, which is the accessibility. Can we get from point 1 to point 2 bar? To go from point 1 to point 2 bar, we would have to travel along the curve, passing through the critical point C at the nose. That would require the specific energy to first decrease to E minimum and then increase again. But in our physical situation, the specific energy only decreases by zero point 0.5 foot due to the ramp situation. It does not decrease all the way to E minimum and then come back up. So to get to the point 2 bar, we would need a much larger bump, one that lowers the specific energy all the way to the minimum and then lets it recover. So, in fact, these theoretical calculations that to reach critical conditions at the top of the bump would need to be approximately zero point 0.9 feet higher, not zero point 0.5 feet as given in this numerical problem. So our bump is only 5 feet over here, so we can't reach the supercritical branch. Now, uh, also, the only accessible state is the point number two, which is the subcritical branch. So Y2 comes out to be 1.72 feet. The downstream water surface elevation is then Y2 plus Z2 equals to 2.222 feet. So notice something interesting over here, that the upstream water surface was at Y1 plus Z1 was 2.3 feet. So even though the bottom went up by zero point 0.5 feet, the water surface actually went down by zero point zero 0.08 feet. This is the classical subcritical response to a rise in the bottom, the surface dips. So we also note that the upstream flow were supercritical. The opposite would happen if the upstream flow were supercritical. The opposite would be happening. So the surface would rise over the bump. The Froude number determines the response. Now, this example beautifully illustrates the power of the specific energy concepts. It gave us the framework for understanding and resolving a non-intuitive result. But what about more general cases where the bottom slope changes automatically? We have a more general equation for the gradually varied flow. So this equation over here, dy over d of x, this equation tells us that the rate of the change of the depth depends on the difference between the friction slope and the bottom slope, and on the Froude number also. So the denominator 1 minus Froude number square is the key. It shows why subcritical and supercritical flows behave oppositely. And when Froude number is less than 1, the denominator is positive, but when the Froude number is greater than 1, it's negative. This sign difference is why subcritical and supercritical flows have opposite responses to the same change in the bottom slope. So this equation is the foundation for analyzing the gradually varied flow profiles, which we will touch on in the next section. But first, we have laid the groundwork. We have seen that energy considerations encapsulated in the specific energy diagram provides a powerful tool for understanding how flows transition from one state to another. And this understanding is also essential for designing channels that smoothly transition between different slopes and cross section. So now, what happens when the driving force of the gravity and the resulting resisting forces of friction are in perfect balance? So that would bring us to our next topic, which is about the uniform depth channel flow, where we will introduce the Manning equation and learn how to calculate the flow in channels of constant depth. So see you next time.